Welcome back, everyone. Ready for another deep dive? Today, we're exploring motion and time.
Two concepts that might seem basic, but trust me, there's a lot more to them than meets the eye.
Exactly. Whether you're brushing up on the fundamentals or just curious to learn more, this deep dive will have something for you. We'll uncover some fascinating insights about how we make sense of the world around us.
We'll be looking at how those seemingly simple concepts, like a swinging pendulum, help change how we measure time.
And we'll see how graphs can tell us so much more about motion than words or numbers ever could.
We're going to break down those tricky relationships between distance, speed, and time, too.
Okay, let's start with something I remember from school. Types of motion. Back then, it all felt a bit, theoretical.
It's easy to miss how elegant these types of motion are, but they really are the foundation of how we understand movement.
Right. First up, motion along a straight line, like picture soldiers marching, or a car on a straight highway.
Exactly. Movement in one direction, no curves, no changes. Now think about circular motion. A dancer spinning gracefully? Or a planet orbiting a star?
Straight lines versus circles. Okay, I'm starting to see a pattern here. What about when motion repeats itself, like a swing?
Ah, that's periodic motion. That back and forth, or clocks ticking, even a guitar string vibrating, it's everywhere.
Wow, you're right. Once you start looking for these types of motion, they really are everywhere.
Understanding them is key, too. We use them to design everything from simple toys to those complex machines we rely on.
So true. It makes you think, how do these types of motion work in nature?
Well, the Earth going around the sun, the moon orbiting the Earth, that's circular motion on a grand scale.
Right. What about periodic motion? Any examples in nature?
Oh, tons. Your heartbeat, for one, the tides rising and falling, the seasons changing, it's all about those repeating patterns.
I'm starting to really get how fundamental these types of motion are. So we've talked about how things move, but how do we describe how fast something is going?
That's where speed comes in. It tells us how quickly something is changing its position.
So if I'm running faster than someone, I'm covering more distance in the same amount of time.
Right. You got it. And there's a formula. Speed equals distance divided by time. So if you run 100 meters in 10 seconds, your speed is 10 meters per second.
Okay, that makes sense. But what about when speed isn't always constant? Like when I'm driving, I'm sometimes faster, sometimes slower.
Great point. That's where average speed comes in. It's
Yeah.
about looking at the whole trip and saying, okay, overall, I traveled at this speed.
Like my average speed on a road trip might be 60 kilometers per hour, even if I was going faster or slower at different points.
Exactly. And remember, those units are important. Kilometers per hour, meters per second, they tell us the relationship between distance and time.
Right. Saying I was going 60 doesn't tell us much without knowing if that's miles per hour or kilometers per hour.
Now, think about your daily life. When do you care about speed?
Oh, all the time. When I'm checking my speedometer, seeing how long it takes me to walk to the store, trying to catch that bus before it leaves. Speed is everywhere. Are there any other real-life situations where speed is really important?
Think about sports, especially track and field or car racing. Speed is often what determines who wins.
Of course. And in things like aviation or space travel, getting the speed calculations right is critical for safety and success.
Absolutely. Even in nature, think about a predator chasing its prey. Speed can mean the difference between a successful hunt or going hungry.
Wow, speed really does have an impact everywhere. It makes you think about time, too. What if we didn't have clocks or calendars? How would we even know what time it is?
That's a great question. For centuries, people relied on nature to track time. Sunrise, sunset, the moon's phases, the seasons changing. They all provided a kind of natural rhythm.
It makes you realize how much we take our clocks for granted. Those early civilizations must have had a very different experience of time.
They did. They observed the patterns in nature, using them to create their own calendars and timekeeping systems.
So basically, they were using natural periodic events to measure time. But how did we get from observing the sun and moon to the sophisticated clocks we have today?
That's where the pendulum comes in. Ever noticed how a pendulum swings back and forth in such a regular way?
Yeah, there's something almost mesmerizing about it.
The time it takes for one complete swing, called the time period, stays remarkably consistent. That consistency is what makes it so useful for measuring time.
Hold on, are you telling me that our clocks today are based on something as simple as a weight on a string?
Well, not exactly. But the principle of that regular pendulum motion was a huge breakthrough in making clocks more accurate. And it all started with a simple observation by Galileo Galilei.
Oh, I know that name. He's the one who made all those incredible discoveries about the planets, right?
That's right. But he also made some important contributions to our understanding of motion and time. The story goes, he was sitting in a church one day when he noticed a lamp swinging back and forth.
And that sparked his curiosity.
It did. He was fascinated by how regular the motion was and started experimenting with pendulums.
Amazing. So from a swinging lamp to unlocking the secrets of timekeeping, it shows how those everyday observations can lead to incredible discoveries.
Absolutely. And from those early pendulum experiments, clockmakers figured out how to build more and more sophisticated clocks, leading to the ones we use today.
So we've gone from observing nature's cycles to harnessing the power of a simple pendulum to create incredibly precise clocks.
It's fascinating how that simple concept led to such a major advancement. What were some of the challenges those early clockmakers faced when they tried to turn a pendulum into a working clock?
One big one was how to keep the pendulum swinging without messing up its regular rhythm.
Because it needs energy to keep moving, right?
Exactly. They had to come up with clever ways to make sure the clock's gears and springs didn't interfere with the pendulum's natural swing.
Sounds like a delicate balance between providing energy and maintaining precision. You got it. And they had to deal with things like friction and air resistance, which could slow down the pendulum over time. Overcoming all those challenges required some seriously ingenious solutions.
It makes you appreciate how innovative those early clockmakers were. They were true pioneers. What were some other major breakthroughs in the history of clocks?
Well, in the early 20th century, the invention of the quartz clock was another big step. Quartz crystals vibrate at a really precise frequency when you pass an electric current through them.
So they were able to use that to make even more accurate clocks.
Exactly. It led to a revolution in timekeeping, highly accurate clocks that were also affordable.
So we've gone from pendulums to quartz crystals, always pushing for greater precision in measuring time. What's the most accurate type of clock we have today?
That would be the atomic clock. They use the vibrations of atoms to measure time, and they're incredibly accurate. We're talking about losing or gaining 1 second every 100 million years.
Wow, that's mind-boggling. From observing the stars to using the vibrations of atoms, we've come a long way. What do you think the future of timekeeping holds?
Now that's a question. Scientists are always pushing the limits of precision, exploring new technologies and materials. Research into optical clocks, which use light to measure time, could be even more accurate than atomic clocks.
It's exciting to think about what they'll come up with next. Okay, so we've covered the basics of motion, the amazing story of how we measure time. But there's one more piece to the puzzle. How do we visualize and understand motion?
Graphs are the key. They give us a way to see the relationships between things like distance and time. It's so much clearer than just looking at numbers in a table.
Intriguing. Tell me more about how these graphs work.
Imagine tracking a car's journey. We could write down its distance at different times, but a graph makes that data come alive.
I'm starting to see the appeal. How do we actually create these motion graphs?
It's called a distance time graph. We start by setting up our axis. The horizontal axis, the x-axis, represents time, and the vertical axis, the y-axis, represents distance.
So time on the bottom, distance going up the side. Got it. What's next?
We choose a scale for each axis.
Mind-blowing. Straight lines for steady speed, curves for changes in speed. Like the graph is telling us a story.
That's a great way to put it. And here's something else. The slope of the line represents the car's speed at that moment. Steeper slope, faster speed.
So cool. We can actually see how the speed changes over time just by looking at the slope at different points.
Exactly. We can even calculate the exact speed by measuring the slope, how much the distance changes for a given change in time.
No way. So we can get real numbers for speed just from the graph. How does that work?
Let's say the line goes up 2 centimeters on the y-axis, distance, for every 1 centimeter on the x-axis, time. If our scale is 1 centimeter on the y-axis equals 1 kilometer, and 1 centimeter on the x-axis equals 1 minute, then the speed is 2 kilometers per minute.
Wow, that's amazing. These graphs are way more powerful than I thought. It's like they unlock a whole new level of understanding.
I know, right? And we can use this concept in so many real-world situations.
Give me some examples. I want to see these graphs in action.
Think about analyzing a marathon runner. By plotting their distance and time, you can see when they were keeping a steady pace, when they sped up, slowed down, even calculate their average speed for different parts of the race.
That would be super helpful for a coach or a runner trying to figure out their best strategy.
Absolutely. Or think about tracking a storm. Meteorologists use these graphs to plot a storm's path, predict its speed and direction, crucial for issuing those timely warnings.
Right, these graphs aren't just theoretical, they're being used to make important decisions that affect people's lives.
Exactly. From tracking athletes to predicting storms, distance time graphs help us make sense of motion in all its forms.
I'm starting to see why scientists and engineers rely on these graphs so much. They're like visual shortcuts to understanding complex data. But hold on a sec. Let's make sure I've got all the key definitions straight. It helps me to really solidify my understanding.
Good idea. Let's recap. First, motion, any change in an object's position over time.
So, a car on the highway, a bouncing ball, even a planet orbiting a star, it's all motion.
Precisely. Now, how fast that object is moving is its speed, the distance traveled over a certain amount of time.
And the formula is distance divided by time. So if a cyclist goes 30 kilometers in 1 hour, their speed is 30 kilometers per hour.
Spot on. And remember, average speed comes in when the speed isn't constant, like on that road trip we talked about. Total distance divided by total time.
Okay, got it. Clear definitions for motion and speed. Now, what about time? It's so fundamental, yet kind of hard to define.
You're right. Maybe the easiest way to think about it is as the sequence of events from the past through the present into the future. We measure it using units like seconds, minutes, hours, days, and years.
And we use clocks and calendars to keep track of it all. But what makes certain events, like a pendulum swinging, so useful for measuring time?
It's all about their predictability and regularity. We call them periodic events because they occur in a consistent, repeating cycle.
Right, like the ticking of a clock or the Earth rotating.
Yeah.
Each cycle takes a specific amount of time, the time period. So for a pendulum, it's the time for one full swing back and forth.
You got it. The consistent time periods of these events are what let us create clocks and calendars to accurately measure time passing.
This has been such an insightful deep dive so far. It's amazing how connected motion and time are and how fundamental they are to understanding how the world works.
It really is. And we've only just scratched the surface. There's a whole universe of fascinating phenomena waiting to be explored when it comes to motion and time.
Okay, we've covered different types of motion, the history of timekeeping, and how to understand distance time graphs. What else is in store for us on this deep dive?
Well, next up, we're going to explore the world of forces, those invisible things that make objects start moving, stop moving, or change direction.
So forces. That sounds intriguing. I'm ready to uncover the secrets behind these hidden influencers of motion.
It's going to be a fascinating journey. Buckle up.
So we've talked about how distance time graphs can tell us if speed is constant or changing, and how the steepness shows us how fast something's going. That's already pretty cool, but can these graphs do even more?
Oh, absolutely. They're like multi-purpose tools for understanding motion. For example, let's say the line on our graph isn't straight, but curves upward. That tells us the object is accelerating, its speed is increasing over time.
So, like when a car starts moving from a stoplight, the line on the graph would curve up as it gets faster.
Exactly. And the opposite is true, too. A downward curve means the object is decelerating or slowing down, like a car coming to a stop at a red light.
Makes sense. So straight lines for steady speed, curves for changes in speed. It's like the graph is telling us a story about the motion.
Precisely. And get this, the slope of the line on the graph, it actually shows the object's speed at that exact moment. The steeper the slope, the faster the speed.
Whoa, that's so cool. So we can see how the speed changes over time just by looking at the slope at different points.
You got it. And we can even calculate the exact speed by measuring that slope. It's like rise over run, how much the distance changes for a given change in time.
Wait, so we can figure out the actual speed just by looking at the graph. How does that work?
Imagine a part of the graph where the line goes up, say, 2 centimeters on the y-axis. That's distance. For every 1 centimeter, it goes across on the x-axis, time. If our scale is 1 centimeter on the y-axis equals 1 kilometer, and 1 centimeter on the x-axis equals 1 minute, then the speed is 2 kilometers per minute.
Wow, that's incredible. I never realized these graphs were so powerful. It's like a whole new level of understanding motion.
They really are. And we can use this idea for all sorts of real-life situations.
Okay, I need some examples. I'm ready to see these graphs in action.
All right, imagine you're analyzing a marathon runner. By plotting their distance and time data, you can see when they were running at a steady pace, when they sped up, slowed down, and even figure out their average speed for different parts of the race.
That would be super useful for a coach or a runner who wants to, improve their strategy.
Exactly. Or think about tracking the movement of a storm. Meteorologists use these graphs to plot the storm's path, predict its speed and direction, which is crucial for getting those warnings out in time.
Right, so it's not just theoretical. These graphs are being used for real-world decisions, decisions that could even affect people's lives.
Exactly. From athletes to storms, distance time graphs are helping us understand motion in all sorts of ways.
It makes sense why scientists and engineers use them so much. They're like visual shortcuts to understanding complex data. But, let's take a step back for a second and make sure we've got all the key definitions down pat. Sometimes having those definitions really helps me get it.
Great idea. Let's recap some of those fundamental terms. First up, motion. Simply put, it's a change in an object's position over time.
So whether it's a car speeding down the highway, a ball bouncing, or a planet orbiting, it's all motion.
Precisely. And to describe how fast an object is moving, we use the term speed, which is the distance traveled over a certain amount of time.
Right. The formula for speed being distance divided by time. So if a cyclist covers, say, 30 kilometers in 1 hour, their speed is 30 kilometers per hour.
Exactly. And don't forget average speed. That's for when the speed isn't constant, like on a road trip where you're going faster and slower at different times. Total distance divided by total time.
Okay, those are good, clear definitions for motion and speed. Now, what about time? It seems so basic, but defining it can be a bit tricky.
It's true. Maybe the simplest way to think of time is as that sequence of events. Past, present, future. And we measure it using units like seconds, minutes, hours, days, and years.
Right, and we use clocks and calendars to keep track of it all.
Mm.
But what makes certain events, like the swing of a pendulum, so good for measuring time in the first place?
It's all about how predictable and regular they are. We call these periodic events because they happen in a consistent, repeating cycle.
That makes sense, like a clock ticking or the Earth spinning. Each cycle takes a specific amount of time, the time period. So for a pendulum, it's the time for one full swing back and forth.
Exactly. And it's because of those consistent time periods that we're able to make clocks and calendars that accurately measure time passing.
This deep dive has been so insightful. It's amazing how motion and time are connected and how crucial they are to understanding how things work.
Absolutely. And we're just getting started. There's so much more to discover about motion and time.
Okay, we've tackled different types of motion, the history of timekeeping, and learned how to understand those distance time graphs. What other amazing insights await us on this deep dive?
Well, next up, we're going to dive into the world of forces. Those invisible agents that cause things to start moving, stop moving, or change direction.
Forces. That sounds fascinating. I'm ready to uncover the secrets behind those hidden influencers of motion.
It's going to be an exciting ride. Get ready.
Welcome back to our deep dive into motion and time.
We've covered a lot of ground, haven't we?
We have, from different types of motion to the evolution of clocks to the power of distance time graphs. And now it's time to explore the world of forces. I've always been fascinated by how these invisible things can influence the movement of everything around us.
Forces are definitely fascinating. They're the unseen hand behind, well, every push and pull, every twist and turn. They explain why things move the way they do and why some things just stay put.
Okay, I'm ready to unlock the secrets of these mysterious forces.
All right, let's start with probably the most familiar force of all, gravity.
Gravity, the force that keeps my feet on the ground and keeps me from floating off into space.
Exactly. It's that force of attraction between any two objects that have mass. The more massive an object, the stronger its gravitational pull.
So the Earth has a much stronger gravitational pull than, say, a feather, because it's so much more massive.
Exactly. And the closer two objects are, the stronger that gravitational force between them. It's why we feel the Earth's gravity so strongly. But the gravity from distant stars has barely any effect on us.
That makes sense. Gravity seems pretty straightforward. It pulls things down.
Yeah.
Is there anything else to know about it?
Well, gravity is just one type of force. There are tons of others at work in the universe, like friction, for example. That's the force that opposes motion when two surfaces are touching.
Oh yeah, friction. Like when I rub my hands together and they get warm, or when I try to push a heavy box across the floor.
You got it. Friction is all around us, and it's incredibly important in our daily lives. I mean, think about it. Without friction, we wouldn't be able to walk or drive or even hold on to things.
Wow, I never really thought about how important friction really is. What are some other types of forces?
Well, there's air resistance, which is a kind of friction that objects experience as they move through the air.
So that's why a feather falls more slowly than a rock.
Exactly. The feather has a larger surface area, which means it encounters more air resistance.
That's interesting. The shape and size of an object can actually affect how it moves through the air. What about forces that make things change direction?
Think about hitting a tennis ball with a racket. The force from the racket causes the ball to change direction.
Right, and the harder you hit the ball, the greater the force and the bigger the change in direction.
Precisely. Forces don't just start and stop motion, they can change its direction too.
This is making me realize all the different ways forces are at work all around us. What other interesting things can you tell me about these forces?
One of the key concepts is that forces always come in pairs. For every action, there's an equal and opposite reaction. It's one of Newton's laws of motion.
Oh yeah, Newton's laws. I remember learning about them in school, but it was a long time ago. Can you give me an example of that action-reaction thing?
Sure, think about jumping off a diving board. When you push down on the board with your feet, the board pushes back up on you with an equal force, and that's what propels you up into the air.
Ah, that makes sense. So the harder I push down on the diving board, the higher I'll go.
Exactly. It's a perfect example of how forces work together. Another example is walking. You push back on the ground with your feet, and the ground pushes forward on you, which makes you move forward.
It's amazing how these simple things we do involve such a complex interplay of forces.
It really is. Forces are those unsung heroes of motion, always at work, shaping and influencing the world around us.
This has been such an insightful journey, exploring the world of motion and time. We've talked about different types of motion, dug into the fascinating history of clocks, and discovered how powerful distance time graphs can be.
And now, we've got a better understanding of how forces work.
It's been great sharing this with you. Hopefully you're feeling a bit more curious about motion and time and inspired to keep learning.
Definitely. I'm seeing the world differently now, noticing how motion, time, and forces are all around me.
That's what it's all about. Remember, this is just the beginning. There's so much more out there to explore.
Well said. Thanks for joining us on this deep dive. Keep those minds curious and keep exploring that fascinating world around you.